Jump, baby, jump. Jump, 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 jump. Jump, baby, jump. Jump, 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 jump. Jump, baby, jump. Jump, 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 jump.
For the next several lectures, our plan is to pretty closely follow section 11.1 and 11.2 of Dumbit and Foote, and then give some brief highlights of the rest of chapter 11. The focus of chapter 11 is all about the theory of vector spaces. So what is a vector space? It's an R module where R is a field F. So this chapter opens with a chart comparing some language that we use when we talk about R modules, where R is any ring, or really when we talked about R modules, almost always R was a ring with identity, and we were talking about unital R modules. But okay, R can be any such ring, and comparing that to what we say when we're talking about the vector space over a field, the special case where R is a field F. So some of the language over on this side should be familiar to you from when you learned linear algebra, even if it was just linear algebra over the real numbers, the special case where F is the field of real numbers. So I just want to quickly go through this to make sure that we're all on the same page when we use language for vector spaces. M being an R module in the special case where R is a field F is the same thing as saying M is a vector space over R, where remember, R is now a field. We'll say little m is an element of our R module M. In the case where your R module is a vector space, we'll usually say that M is a vector in your vector space. For R modules, we talk about alpha being a ring element. For vector spaces, we talk about alpha being a scalar, being an element of the field F. We have this scalar multiplication, this function from F cross M to M, and these field elements are called scalars. N being a submodule of R, well, for vector spaces, we instead use the term subspace. We can take the quotient of two R modules and get a quotient module. We can take the quotient of two vector spaces for the same reason that the quotient of R modules is an R module itself. The quotient of vector spaces is also a vector space. M is a free module of rank R. This we'll come back to more in this lecture. That corresponds to saying that M is a vector space of dimension n. So being a free R module of rank R means that there exists a subset A inside your R module M of size n that is a basis for M. So you have a basis of size n, and that's what it means over here too. That M is a vector space of dimension n means n is the size of a basis of M. And we'll show later in this lecture that if M has a basis of size n, then in fact, every basis has size n. All right, M is a finitely generated R module. That corresponds to M being a finite dimensional vector space. Finitely generated, finite dimensional vector space. Here, this is saying that there exists some finite spanning set for M as an R module. And here, this is saying that there exists some finite set of vectors such that they span M. So in fact, there's going to be a finite basis, as we'll see later in this lecture. M is a non-zero cyclic module. That corresponds to saying that M is a one-dimensional vector space. So cyclic module means that it's something of the form R times A for some A in M. Non-zero, we're just specifying the zero module is also cyclic, but we want a non-zero one because we want it to correspond to M being a one-dimensional vector space. So we don't want to take the trivial vector space in here. So we shouldn't take the zero submodule in here. OK, if phi is a map from M to N, a map between R modules, phi being an R module homomorphism, we've already seen that in the special case where your R module is a vector space over a field, where R is equal to a field, this corresponds to saying that phi from M to N is a linear transformation of vector spaces. M and N are isomorphic as R modules. For vector spaces, we would say that they're isomorphic vector spaces. And now the last one, if we say that the subset A of M generates M, we've seen that that's saying that M is equal to R times A, that everything in M can be written as a finite R linear combination of elements of A. Over in the land of vector spaces, we would say that the subset A of M spans M, which means that every element of M is a finite linear combination of elements of A, or that M is equal to the span of A. So we've been using a lot of this language already. In fact, in Conrad's notes, the notation for R modules matches up a little bit better with what you know from vector spaces already, talking about spanning sets and whether a set in an R module is linearly independent. So this should be familiar already, but I wanted to review it to make sure that we're all on the same page. So Dummett and Foote write, for the rest of this chapter, anytime when they write F, F is going to be a field, and anytime they write V, V is going to be a vector space over this field F. So we're going to keep these conventions for the next several lectures. So I'll pause and erase, and then I'll get started with the core material about vector spaces. Next, I want to talk a little more about notation. We'll say a subset S of our vector space V is a set of linearly independent vectors if anytime you have a relation alpha1 v1 plus alpha2 v2 plus alpha n vn, where the alphas come from your field F and v1 up through vn come from your set S, then alpha1 equals alpha2 equals alpha n equals 0. That this matches up exactly with what we talked about when we talked about the presentation of modules from Conrad's notes, that linearly independent means no non-trivial relations. All right, so this is review. A basis of V is an ordered set of linearly independent vectors that span V. So that's what I want to emphasize, is the orderedness of it. So we have been talking about a basis as being a spanning set that is linearly independent. But what I want to do here is say that we're going to count two bases as being different, even if one is just a rearrangement of the other. And we're sometimes going to use the term ordered basis if we want to emphasize this property that two bases are going to be different if one is just a reordering of the other. One reason for doing this is that an application that we're going to see at the beginning of the next lecture is going to involve counting all of the different bases for a particular vector space. So if we want to count these things, then it really doesn't matter whether we consider two bases to be the same or different if one is a rearrangement of the other. Another reason is that starting in the next lecture, the focus of section 11.2 of Dummett and Foote is going to be taking a linear transformation and representing it as a matrix. So what that's going to involve is if you have a linear transformation from V to W, we're going to pick a basis for V and pick a basis for W, and we're going to use those bases to write down our matrix. So it's going to matter what the ordering of this basis looks like. So we really do want to emphasize that bases count as being different if one is just a reordering of the other, because we want to understand things like you start with a linear transformation. If you change from one basis to another, how does the corresponding matrix change? So that's the kind of thing we want to talk about. So we're emphasizing this orderedness. OK, so the first thing that we'll prove is that if you have a set, let's say script A, of vectors that span your vector space V, but no proper subset of A spans V. So this is a spanning set, but if you leave out any individual vector, you're no longer a spanning set, then A is a basis of V. If you have this minimal spanning set property, you are automatically linearly independent. So in particular, what does this mean? What is a free R module is an R module that has a basis. So in particular, any finitely generated vector space over F is a free F module. So that's a consequence of this result. And before I prove this, I just want to point out something we've already talked about, which is this statement is just not true for a general R module. For example, we talked about the setting of the Z module Z. Z is a Z module, and the set 2 and 3 spans Z. No proper subset of this set spans Z. Like if you take just 2 or just 3, you don't span Z. But this set does not form a basis because 2 and 3 are not linearly independent. It is easy to write down a non-trivial relation, 3 times 2 plus -2 times 3 equals 0. So proposition 1 is just not true for a general R module. OK, the second part, that a finitely generated vector space over F is a free F module. Z is a free Z module. It does have a basis. You can't find one inside the set 2 and 3, but there is a basis if you just take 1. We saw a different kind of problem that happens for R modules, that if you take the ideal generated by 2 and 1 plus the square root of -5 inside Z adjoint square root of -5, that is a finitely generated Z adjoint square root of -5 module. But it's not a free Z adjoint square root of -5 module. There just is no basis for this Z adjoint square root of -5 module. The idea is that there is no spanning set of size 1, but any set of size 2 or greater cannot be linearly independent. So there is no linearly independent spanning set. So this just is not a free R module. So this proposition that we're about to prove is really showing now how for the vector space over a field F, where we have some certain properties that are nice that are just not true for a general R module where the situation can be more complicated. All right, so I'll pause and erase, and then we'll prove this proposition. Let's prove this proposition. We're starting with this set of vectors that spans V, and we're assuming that no proper subset of it also spans V. We want to show that it's a basis, which means that it's a spanning set that's linearly independent. So all we need to do is need to show that these vectors are linearly independent. So we're going to write down a relation. We'll suppose that alpha1 v1 plus 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 alpha n vn is 0, where not all alpha I are equal to 0. And we're going to find a contradiction. We're going to assume that this set of vectors is not linearly independent, and we're going to get a contradiction. OK, so one of these alpha i's is not 0. If we rename the vectors, if we reorder them in some way, we can suppose that alpha 1 is not 0. So that renaming, reordering idea is going to come up more in this lecture. So if alpha 1 is not 0, we can divide by alpha 1 and subtract. We can divide by alpha 1 and move everything else over to the other side. So that means that v1 is equal to minus 1 over alpha 1 times alpha 2 v2 plus 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 alpha n vn. We've actually already seen this argument pretty much exactly when we showed that when we were talking about R modules and showed that if you have a vector space over a field, being linearly independent was the same as not being able to write one of your vectors as a linear combination of the others. OK, so anyway, this should feel familiar. Now, you know that v1 can be written as this linear combination of v2 up through vn. So what does that tell us? If you take the set of vectors v2 up through vn, this set also spans v. Why? Well, you know that anything in v can be written as a linear combination of v1 up through vn. And the claim now is that you don't actually have to use v1. So you take whatever vector, you write it as a linear combination of v1 up through vn. And then every time you see v1, you replace it with this expression here using star with the right-hand side, which is a linear combination of v2 up through vn. So what we're seeing is any linear combination of v1 up through vn can be written as a linear combination of v2 up through vn, replacing every v1 with this expression on the right-hand side of star. But this is a contradiction now, because we started by saying that v1 up through vn spans v, but no proper subset spans v. And here we're saying that we found a proper subset that also spans v. So this is a contradiction. So what does that mean? These vectors actually were linearly independent, which means that they're a linearly independent spanning set. So A is a basis of V. All right, so now let's prove this second part, that any finitely generated vector space over F is a free F module. So we just have to prove that a finitely generated vector space V over F has a basis. So it's finitely generated, so we know there's a finite generating set. So let's just take one. V is a finitely generated vector space over F. We're going to take any finite generating set. Either that set is already a basis, or if it's not a basis, what that means is that it's not linearly independent. So what that means is, okay, you have your finite generating set. Set that equal to A. If it were the case that no proper subset of this finite generating set spanned V, then it would be a basis. So what that means is either you have a basis or some proper subset of this finite generating set also has to span V. And what's true about that proper subset is it has smaller size. So we have two possibilities. Start with your finitely generating set. Either it's a basis or there is a proper subset of it which has smaller size that is also a generating set. Take that proper subset of smaller size. Either that's a generating set, or, either that's a basis, or if it's not, there has to be some proper subset of it that spans V that also has even smaller size. So every time you go through this process, you either get a basis or you get an even smaller generating set. And the set that you started out with, the generating set you started with, was finite. So you can only do this thing where you take a proper subset and a proper subset and a proper subset, where the size goes down each time. You can only do that finitely many times. And in the end, you have to have some set that is still a generating set and no proper subset generates your vector space, which means by the first part of this proposition that you have a basis. Okay, so start with any finite generating set. Inside it, you can find a basis by just applying the first part of this proposition. All right, so I'll pause and erase, and then I'll say that last thing that I said a little bit more formally. Proposition 1 almost immediately leads to this corollary, which says if you have a finite set A that spans V, then A contains a basis of V. So formally, how does that proof go? A contains a subset such that no proper subset of it spans V. By proposition 1, that is a basis. Why does A contain such a subset? Well, that's what I was just saying in this explanation, that either A itself contains no proper subset that spans V, or it contains a proper subset that spans V that's smaller, and you take that one. And then either that's a basis, or it contains a proper subset that spans V, and you take that one. And you can only do this finitely many times because this set A that you started with was finite. All right, so I want to point out this corollary is not true for a general R module. We can use the same example that we talked about earlier. If R equals Z, M equals Z, Z is a Z module. The set A, consisting of 2 and 3, is a finite set that spans our R module Z, or Z module Z, and it just doesn't contain a basis. There's no basis consisting of a subset of 2 and 3. So the last thing I want to do in this video is talk about an example that's related to a homework problem that you've already done. So F is a field. Let's take a polynomial f of x that's monic, x to the n plus an minus 1, x to the n minus 1, plus a1x plus a0. F bracket x is a vector space. And the ideal generated by our polynomial f is a subspace. So this is easy to check that these sets satisfy the axioms of a vector space. We have seen that if you have an R module M and a submodule N, that the quotient M mod N is also an R module. So if you take the special case where R is a field, you have the quotient of vector spaces is also a vector space. So the quotient f bracket x mod the ideal generated by this polynomial is also a vector space. And now what do elements of this quotient look like? What is a basis for this vector space? So by the division algorithm, you take any polynomial in f bracket x, and you can write it as q of x times f of x plus r of x, where either r of x is 0 or the degree of r of x is less than n, the degree of f of x. So q of x times f of x is always in the ideal generated by f of x. So if you start with any polynomial a of x and you want to know what coset of this ideal is it in this quotient space, you can see that it's in the same coset as r of x. So what does that mean? Every element in this quotient space has a coset representative, r of x, that has degree at most n minus 1. Okay, so I'll pause and erase, and then we'll talk a little bit more about these coset representatives and see a very nice basis for this quotient. We've seen that in this quotient vector space, f bracket x mod the ideal generated by the polynomial f, every coset is represented by a polynomial of degree at most n minus 1. Let's take two such polynomials and see that if they're in the same coset, they must actually be equal. So suppose r of x and r prime of x are two polynomials of degree at most n minus 1 that lie in the same coset in this quotient space. Then what's true about their difference? It's in the ideal generated by f of x. What else is true about their difference? The difference has degree at most n minus 1. But what things are in the principal ideal generated by f of x? It's just things of the form f of x times something. And in particular, all of those polynomials have degree at least n, except one, which is 0. So all of the things in the ideal generated by f of x have degree at least n, except 0. Here is something in this ideal that has degree at most n minus 1. So it has to be 0. So what are we seeing? That every coset is represented by some polynomial of degree at most n minus 1, and each polynomial of degree at most n minus 1 represents a different coset. No two of those cosets are the same. So what does that mean? The elements 1, x squared, up to x to the n minus 1, where this bar denotes what we're doing is we're taking the element in f bracket x and looking at its image in this quotient, that these elements span this quotient space because every element of this quotient space is a linear combination of these elements. It's represented by some polynomial with degree at most n minus 1. We want to actually say that these form a basis. So we have to also see that they're linearly independent. And one thing we could do is try to write down a relation where we take linear combinations of these and set it equal to 0 and then show that all the coefficients are 0. But it's a little easier to use this proposition 1 that we proved. Here's a set that spans this vector space, and no proper subsets span this vector space, because if you leave something out, then you're missing a polynomial of degree at most n minus 1. And every polynomial of degree at most n minus 1 represents a different coset. in this quotient. So no proper subset spans this vector space. So by proposition 1, this set of elements forms a basis for this vector space. We didn't really have all this language at the time, but this is basically the conclusion of exercise 1 in section 9.2, which was on homework 4. So I encourage you to go and look back at what we did in this exercise and compare it to what we're doing here.